Hello students, guess who this is? Correct, it's your Professor Dr. Mink, and this is our lecture on content from Chapter 9, which will be broken into two main components, trap routines and then subroutines. You should understand that a trap routine is simply a system subroutine. It is a subroutine that lives in system space and has certain privileges that you wouldn't have with subroutines, but we'll get into that as we move forward. So let's get started. First topic is a term that's very important, system call. And there are certain operations that require certain protections and specialized knowledge of I/O device registers, sequence of operations, etc. And input-output resources are shared among multiple users and programs. So a mistake in accessing these resources could have significant impact. And there's also the matter of abstraction. Not every programmer needs the level of detail for basic I/O that's coded into a system call. So to perform a system call, we provide service routines, also called trap routines in the LC3. And these are part of the operating system. And they perform privileged operations. A system call is invoked by code in a user program, and then the operating system handles the specific task in the system call and then returns control to the user program. In the LC3, we call these trap mechanisms or trap routines, and they are system subroutines. And although we're going to cover system subroutines or trap routines first, and then we will cover user subroutines, they are very similar in the mechanics. And the one difference is where they live. The trap routines or system subroutines live in system space. And there's one extra step in invoking those routines, and that's the trap vector table, which we're going to get to very quickly. But the mechanism is very similar. So the LC3 trap mechanism includes a set of service routines that are part of the operating system. And we know that user space available for user programs, begins at hex 3000. So the operating system exists between hex 0000 or hex 0 and user space. So we have up to 256 trap routines. And to access the trap routines, we have a trap vector table, which is also called system control block, is the more generic name for this. And the trap vector table is a table of starting addresses for the actual trap routines. And it starts at hex 0 through hex 00FF in memory. Now the trap instruction is the actual program that resides within the operating system. And we have an 8-bit trap vector name for one of the 256 service routines. So when you see a trap X25, that 25 is actually 8 bits, because remember, 4 bits of binary for 1 bit of hex. So hex 25 is an 8-bit trap vector address. So once we get to the list of starting addresses in the system control block, aka the trap vector table, we go to that address in the operating system. We execute the entire system subroutine or trap routine, and then we have a linkage back to the user program, which we'll get to in a second. And other than the address stored in the trap vector table, which is part of the operating system, the rest of this whole trap mechanism works very similarly to the user subroutines that we'll learn next. Here's some information I took from your textbook, and it shows the trap vector table. And so, for example, trap X21 is the character output service routine. And so the X21 is the address in the trap vector table that then stores at that address, it stores the hexadecimal memory address of the first instruction in the output service routine, which in this case is at hex 0430. The keyboard input service routine, which is a trap X23, begins at hex 04A0. So the difference is you don't go directly to the starting instruction of the system subroutine. You have a trap vector address, which holds the starting address of the system subroutine, aka trap routine. Here we have the syntax or the bit pattern for the trap instruction. The opcode is 1111. Bits 8, 9, 10, and 11 are unused or irrelevant, so they're all zeros. And then the bits 0 through 7, 8 bits, specify the trap vector. So if it was a trap X25, you'd have 0, 0, 1, 0, 0, 1, 0, 1. Okay, sorry, I had to do a little bit of hex to binary in my head. So the trap vector identifies which system call to invoke, and it refers to an address in the trap vector table. The trap vector table is stored in memory, and it starts at the very beginning of memory and goes to hex 00FF. And the 8-bit trap vector table is a 0 extended. It's not a 2's complement, it's 0 extended to 16-bit memory address. So even if bit 7 is 1, it's not a sign extended value as we had in 2's complement. So we look up the starting address from the table, the trap vector table, and we then place the address stored in that starting address into the program counter. And you'll see that we have a return, which is a jump bar 7, as the last instruction in the trap vector, in the trap routine. So the trap instruction causes the service routine to execute and then exit. It changes the program counter to the starting address of the service routine based on what's stored in the trap vector table. And it also provides a way back, which is called a linkage, and that is a return. And so when you call a trap routine, you'll find that the program counter value is transferred to register 7. And register 7 must be preserved and restored if the trap routine uses R7. And you'll see that. I have several demonstrations planned that will solidify understanding of this trap vector table, jumping to the trap routine, and then returning. In this diagram, we illustrate the trap mechanism operation. So somewhere in our user program, we have a trap call to trap x23. So we go to the address hex 0023, and at 0023, that's part of the trap vector table, also referred to as a system control block, a more generic term. And the address stored at hex 23 is hex 04A0. So 04A0 is actually the first instruction in the service routine. And the service routine, which is labeled B in this particular case, ends with a return, which is also a jump R7. Return and jump R7 are opcode 1100, and you could see 111 for 7, but a return is simply a hard-coded jump R7. They do exactly the same thing. So when the trap routine in user program A is encountered, part of the transferring to the service routine is to move the program counter from the user program into R7. And we'll talk later about preserving R7 and then restoring it. Here we have the micro instruction diagram, which shows the current program counter gets stored in R7, and then we take a 0 extended bits 0 through 7 get 0 extended in the instruction register and fed to the memory address register, which then accesses that memory, and the value stored at that memory. So we're in the trap vector table now. Then the value stored gets transferred to the memory data register, and then that becomes the new program counter value. So we've stored the linkage, the program counter, from the calling routine or the calling program into R7. And then we've gone to the trap vector table and moved or copied the address from the trap vector table, the address of the first instruction of the trap routine, into the new program as the new program counter value. And then the last instruction in that trap routine has to be a return or a jump R7. And as I mentioned earlier, and I'm going to continue to mention, we have to, if that trap routine uses R7, we need to preserve it and then restore it, or we would lose the linkage back to the calling program. So here we're covering the linkage back, which is the return. LC3 assembly language lets us use return, the mnemonic return, in place of a jump R7. Jump allows us to jump to an address stored in any of the registers, but return is a hard-coded jump R7. And that's how we transfer control back following the trap routine. The end of every trap routine and every subroutine that we code in the next section of this class will end with a return. Now, as I mentioned earlier, if the service routine does not preserve R7, which means if it uses R7, the first thing we must do is preserve R7, store it somewhere in memory, and then restore it, load it back into R7 right before the return, or we break the linkage back to the calling program. This is really important in both trap routines. Well, it's not really important in trap routines because they're system subroutines, and this is absolutely positively taken care of. It's going to be more important than when we start writing system subroutines. And every class I teach, we often have a student or one or two or three or whatever that uses R7 and forgets to preserve it. It's actually a very valuable learning experience to have this happen, because you lose the linkage and you never get back from the from the subroutine. Here we have a list of the trap routines, their assembler names, and their address in the trap vector table. GetC, which reads a single character without echoing. It's the address of the start of that trap routine is stored at hex 0020, which is in the trap vector table, also called the system control block. Out is stored at hex 0020. I'm sorry, its starting address is stored in the trap vector table at hex 0021. Puts, its starting address is stored at hex 0022, in 0023, and halt 0025. So the trap vector table at hex 20, 21, 22, 23, and 25. Actually should not call them 25 because it's not decimal 25, it's 25 in hex. You know what I mean. Those 5 addresses in the trap vector table hold starting addresses of system subroutines. So, and what I'm going to do in a video next is, well, not next, but after this lecture, I'll create a video that shows the actual trap vector table, and then we will jump to the address for one or more of those trap routines as stored in the trap vector table, and you'll see the actual code for the trap routine. I created a video and placed it into this week's Canvas module with this code, and I run it and demonstrate the trap vector table's role in the trap routine mechanism. And you'll see it, how it transfers the program counter to the value stored in the trap vector table associated with the trap routine, and then executes that routine, all the while saving the linkage back in R7 and then the return. So that would be a good time to, excuse me, pause this video and go watch that other video. Okay, it's called Trap Demo. In this slide, we're going to dissect the output service routine, or out. And you're going to see this is a trap X21, and at hex 0021 you'll see the address 0430 stored, which is the start address for the output routine. And you'll see the first thing it does is it stores R7 in a labeled location called save R7, and it stores R1 because we're going to use R1 and R7. And actually, I'm looking at it now, it's not going to use R7, but that's actually a very good habit to get into. And then the last two things before the return, the last two instructions before the return, were restoring R1 and R7, and then we hit our return. And here's another table showing the trap routines and their assembler names. Remember, the vector is the address in the trap vector table where the starting address for the output routine, I'm sorry, for the trap routine is stored. So it is critical that the state of your program can be exactly restored after the trap routine is called, executes, and returns. So the values in registers have to be saved if they'll be used or destroyed by the service routine, or we'll need to use the value after the service routine. So who should save what? So the caller of the service routine only knows what it needs later, but it may not know what gets altered by the service routine. Remember, abstraction. In order to use a service routine, you just need to know what the argument is and what it will return. And in most cases, it's an address in R0. So most of the onus of preserving the state of the calling of the program that calls the service routine falls on the service routine. It knows what it alters, but it doesn't know what will be needed later by the calling routine. So when in doubt, preserve it. So it wouldn't be a bad habit for every service routine to store every register and preserve every register, and then restore them at the right before the return. But that doesn't happen. But I'm going to suggest that, or something close to that, when we get into our own subroutines. So here we have an example snippet from a program that has a loop in it. And it looks like a count controlled loop, and it's using R7 as the counter. And as long as R7 is positive, it will continue to loop back up to the instruction labeled again, which is a trap X23. So what's wrong with this routine? Can you tell me what's wrong with this routine? Probably not a great idea to use R7 when we know R7 is going to be the linkage back from the trap routine, and R7 will hold a specific value as we call the trap routine. Look, that's the last instruction at the bottom of the loop, in the body of the loop. So R7 is going to hold a value, and then when we get to trap X23, as long as the counter is positive, we'll be writing the program counter address, the address of that add R0, R0, R6 into R7, and we will be compromising the value of the counter. So here we have some suggested protocols for saving and restoring registers. The first one is called call-e-save, where the called routine, before starting, saves any registers that'll be altered within the calling program, and then right before the return, restore those same registers. That's what we saw earlier with store R7 in a value in a labeled memory address called save R7, and we stored R1, and then before the end, right before the return in that routine, we restored them with load. And then the second protocol is called caller save, and the calling routine saves registers destroyed by the routines that we call. So if we need those values later, so in the example we just used, we would have saved R7 before we called that trap routine. Okay, we want to save R0 before we call trap X23, because the return value of trap X23 is deposited in R0. So it will overwrite whatever's in R0. Here are some questions we should ask ourselves before moving forward. Can a service routine call another service routine? What do you think? Obviously, if we were together in class, we'd be talking about this and I'd be calling upon you, but that's kind of hard in this modality. So yes, a service routine can obviously call another service routine, and that does happen. So yes, and if yes, are there anything special the calling service routine must do? Yes. If you're calling a service routine that has a return value in on R0, or you need to preserve R7, if you're using R7 for something other than a linkage, yeah, you got to preserve all of that before you call that service routine.